Hey there, let's talk about something that's at the absolute core of science measurement. It really all comes down to being honest with our numbers, and that starts with a challenge that every single scientist has to face. Think about it this way: some things are just certain. You count the eggs in a carton, and what do you get? An exact number. It's 12. Not about 12, not 12-ish. It is exactly 12. But the second you stop counting and start measuring, say, the amount of liquid in the cylinder, a little bit of uncertainty just naturally creeps in. Is it 21.6 milliliters, maybe 21.5, or 21.7? That tiny bit of doubt, well, that's what measurement is all about.
So how do scientists handle this? Do they just ignore it? Nope. They actually came up with a really smart system to communicate exactly how certain or, uncertain their measurements are. And this entire system is built around an idea called significant figures. All right, let's go back to our graduated cylinder. We look at it and we say, okay, that's 21.6 milliliters. But that number isn't just a number. It's actually a story. It's telling us about the tool that was used, and it's telling us about the confidence of the person who took the measurement. Let's break that story down a little bit. We can see for sure that the liquid is past the 21 milliliter mark. So those digits, the 2 and the 1, we're certain about those. But that last digit, the 6, well, that's our best guess. It's an estimate of where the water level falls between the lines. It's the uncertain digit. And yet all three of these digits, the 2 certain ones and the 1 uncertain one, they are all considered significant. And that brings us to the official definition. Significant figures are basically all the digits in a measurement that actually mean something. They're the numbers that carry real, useful information about just how good your measurement was. You could say it's the scientific way of being totally honest about your data. Okay, this seems pretty straightforward, right? All the non-zero digits are significant. Easy. But what about zeros? This is where things get a little tricky, because sometimes a zero is just a placeholder, and other times it's one of the most important parts of the measurement. So we need some rules. This table lays it all out perfectly. First, you've got captive zeros, the ones that are sandwiched between other important digits, like in 1.01. Those always count. Then you have leading zeros, like in 0.05. They're never significant, they're really just there to show you where the decimal point is. Now, trailing zeros after a decimal, like in 2.00, are super important. They're always significant because they're telling you that you measured with precision all the way out to the hundredths place. The really tricky one is the last one, trailing zeros before a decimal, like in 1300. Are those zeros measured, or are they just placeholders? We can't be sure just by looking at it. And this brings up a fantastic real-world example. A few years back, the U.S. Census reported the population down to the single last person. But seriously, think about that for a second. With people being born and dying every moment of every day, is it really possible to know that number with that much certainty? Probably not. It's a lot more reasonable to say the population is about 317 million, right? That acknowledges the uncertainty. So context is everything. So we've got a handle on how to spot significant figures. But what happens when you have to start doing math with these uncertain numbers? You've got to be careful that your final answer doesn't somehow look more certain than the numbers you started with. This right here, this is the golden rule. You have to remember this. It's like saying a chain is only as strong as its weakest link. In science, your calculated answer can only be as good, as precise, as your least precise measurement. Claiming anything more is just not being honest with your data. And to make sure we follow that golden rule, there are 2 different sets of rules you gotta know. For adding and subtracting, it's all about the number of decimal places. Your answer has to be rounded to the same number of decimal places as the measurement with the fewest. Simple. But for multiplying and dividing, you switch gears. You have to look at the total number of significant figures, and you round your answer to match the number with the fewest sig figs. Let's see how this works. Say you subtract 421.23 grams from 486 grams. Your calculator's going to spit out 64.77. But wait, you got to look back at your starting numbers. That 486 has no decimal places. Its uncertainty is in the ones place. That means you have to round your answer to that same level of uncertainty. So the correct and more honest answer is 65 grams. Okay, now for multiplication. Let's multiply these 2 lengths. The calculator gives us this long number, 4.11708. But again, we have to check our weakest link. The measurement 6.6 centimeters only has 2 significant figures, while the other number has 4. That means our answer can only have 2 significant figures, so we round our result to 4.1 square centimeters.
Okay, we've gone through all the rules for how to report our numbers. Now let's kind of zoom out and talk about two really big ideas that define the quality of any measurement: accuracy and precision. Now, they sound like they could be twins, but in science, they mean very different things. So what's the difference? Accuracy is all about hitting the target. It's how close your measurement is to the actual true value. Precision, on the other hand, is all about consistency. It's how close a bunch of your measurements are to each other, even if they're not anywhere near the true value. The absolute best way to picture this is with an archery target. This is the goal. This is what we're all aiming for, right? Your shots are all bunched up together, that's precision, and they're all right in the middle of the bullseye. That's accuracy. Perfect. Now check this out. The arrows are all grouped together really tightly, so this archer is very precise, very consistent. But they're all way off target. This is a huge clue that there's some kind of systematic error, like maybe the sights on the bow are crooked. The shots are repeatable, but they're repeatably wrong. And then there's this. This is the worst-case scenario. The arrows are just all over the map. They aren't consistent with each other, so they're not precise, and they aren't even close to the bullseyes, so they're not accurate either. This data is pretty much useless. Okay, let's swap out arrows for something a little more down to earth. Testing cough syrup dispensers. The target is 296 milliliters. Dispenser number 1 is giving really consistent results, but they're all around 284 milliliters. So it's precise, but it's not accurate. Dispenser number 2 is all over the place, but the numbers are kind of scattered around the target. So it's sort of accurate on average, but not precise at all. But then look at dispenser number 3. Now that's our winner. All of its measurements are packed tightly right around the 296 milliliter target. It's both accurate and precise. So why? Why have we spent all this time on significant figures and rounding rules and the difference between accuracy and precision? It's because science, at its very heart, is about finding the truth. And you can't do that without being completely honest in how you report your numbers. It really all boils down to this one simple goal. Following these rules isn't just about passing a test. It's about scientific integrity. It's about making sure that when you share a result, you're also sharing how confident you are in that result. That's the foundation of science we can all trust. And that leads me to one last thing to think about. We are surrounded by data every single day, in the news, on social media, in ads. So the next time you see a very specific number, just take a second and ask yourself, how was that measured? Is that number really as certain as it looks, or is it just an estimate hiding in plain sight? Something to think about. Thanks for tuning in to this explainer.